Hello all. I am Vignesh, working as an assistant professor in the Department of EC of Kongi Engineering College. So today we are going to discuss about how does the low pass RC circuit will behave whenever we are applying a step input. So before getting into the topic, we'll understand first how this series RC circuit will be working as a low pass RC circuit. So this low pass RC circuit will consist of one resistor and one capacitor. They are connected in series, and we are taking the output from this capacitor and we are applying the input to the series RC network. And we know the reactance of the capacitance is nothing but Xc equal to 1 divided by 2 pi Fc. Now I am considering the case that I am going to apply the low frequency signal, that is F is equal to 0. So whenever F is equal to 0, according to this formula, my Xc value will become infinite. That is, my reactance of the capacitance will become infinite, which means that the capacitor is open circuited. So whenever the capacitor is open circuited, there will not be the current flow through this resistor, and because of that you will not be having any voltage drop across this resistor. And in this case, whatever the input voltage you are applying, the same you will be getting at the uh, output. That is, the output voltage is nothing but the input voltage. That is, we can conclude that in whenever you are applying the low frequency signal, whatever the signal which are available in the input, the same will be passed to the output side. In this way, the low frequency signals are passed to the output side. Now we are considering to the high frequency signals. So that is, f value is infinite. So whenever the f value is infinite, according to this particular formula, your Xc value is 0 and your capacitor will become short circuited. So whenever you are taking a voltage across the any short circuited terminal, the voltage value will become 0. That is, whenever you are passing the high frequency signal, will not be getting any output in the output side. In that way, this particular RC circuit will attenuate or avoiding the high frequency signal to be available in the output side. Okay, now we can move on to the analysis part. So in this formula you can write according to the voltage division rule. So A is nothing but a gain of the low pass RC circuit, and here you can cross multiply this RCS and you can cancel out the things, so that finally you will be having the values 1 divided by 1 plus RCS. Okay, then S can be replaced by 1 by j omega. Again, omega can be replaced by 1 by 2 pi f, and you are taking the magnitude of the gain value. So you need to take the magnitude of this particular term, and it will end up with this expression. Now, if you want to find the cutoff frequency or 3 dB frequency, you need to substitute the magnitude value as 1 by root 2. So substitute the A value as 1 by root 2 and simplify this particular expression, so that you will be ending up with f2 values 1 by 2 pi rc. This is the cutoff frequency formula. Now from this you can say that 1 by 2 pi rc is equal to 1 by f2. If you are exchanging the things to the left hand and right hand side, you will be end up with the 2 pi rc can be replaced by 1 by f2. So here you can replace 2 pi rc by 1 by f2. So a value will become 1 divided by 1 plus j into f divided by f2, and from this you can write the magnitude of the gain. So this is nothing but the expression for the magnitude of the gain of the low pass filter. Now we will move on to the step input voltage. So this is nothing but your step input. So step input is nothing but so whenever the t value is less than 0, will not be having any magnitude, or in other words the magnitude value is 0. And what happens when the time t value is greater than 0? In that case you will be having the input voltage value as, let us say, the input voltage is A. Now what happened to t value exactly equal to 0? Because less than whenever t less than 0, you are getting a 0 magnitude, and whenever t greater than 0, you will be having the voltage or magnitude value as A. Now what happened exactly at t equal to 0? Your input voltage will jump from 0 to A. Okay, this is a sudden change. This is a behavior of a step input voltage. Okay, now we can move on to how the capacitor will behave, or in other words low pass RC circuit will behave whenever you are applying the step input voltage. So now this is nothing but your low pass RC circuit. So whenever you are applying the uh, input signal, which is a step signal, what happens at t equal to 0, your input voltage will jump from 0 to a. So let us call this particular magnitude value as a. Okay, now what happened to this case? So we know that the capacitor will not allow the sudden change in the input voltage. So whenever you are applying the signal exactly at t equal to 0, your input jumps from 0 to a. So here input jumps from 0 to a. Whenever it reaches the input, here also the input jumps from 0 to a. But this particular capacitor will not allow the sudden change in the voltage. So hence at t equal to 0, the capacitor will behave like a short circuit. It will not be allow any sudden change in the voltage, and it tries to maintain the zero voltage level. That is zero voltage level in the sense, in other words, you can say that it is a short circuited terminal. So so initially you can see that this is a response curve of a low pass RC circuit. So this is the input and this is output. In the output you can see initially uh, the value of the output is 0, and as the time proceeds, you the capacitor will tries to charge slowly to the input value of A. So this is the behavior of a capacitor or a low pass RC circuit. Now, from that particular figure, you can say that the initial voltage is 0 volt, because the initially the capacitor will not allow the sudden change in the input voltage. So the capacitor will be maintaining its 0 voltage level. Now, finally, what happened? It will reach to the input voltage. Here, input voltage I am considering it as a volt. So my initial voltage is 0 volt and my final voltage is A volt. And I know the general expression for the charging of a capacitor, which is nothing but V naught of t equal to V final. Here F stands for final. V final plus Vi. Here it is a V initial voltage. So V final plus V initial minus V final into e power minus t by tau. Here tau is the time constant. So the value of tau is nothing but a RC. Okay, and substitute the final value as a, initial value is 0, so we'll end up with this particular expression, and 0 minus a is nothing but minus a, and you are taking a as a common from these two terms, so you'll be having a into 1 minus e power minus t by tau. This is the output expression for the response of a low pass response of a step signal to the low pass RC circuit. Okay, now you can see this diagram. This is nothing but my input signal, this diagram, and this curve, you can see that this is my output signal. Okay, now I am going to analyze one particular term, which is nothing but a rise time. So you can see the definition of rise time here. It is actually time taken by the output response curve to jump from 10% to the 90% of its final steady state value. Here steady state value is nothing but your A, your applied input voltage A. So 0.1 A, which means that it is a 10% of the steady state value. 0.9 A means it is a 90% of the final steady state value. So the rise time is nothing but how much amount of time required for the response to jump from 0.1A, that is 10% to the 90%. So this time difference you need to calculate, that is nothing but a rise time. We'll see how we can calculate this rise time in the upcoming slide. So this is the expression we have derived, V naught of t, and this is nothing but a response of a low pass RC circuit whenever you are applying the step input. Uh, Here if I want to calculate the how much amount of time the output response is taking to achieve 10% of the final value, in order to calculate that you need to substitute the output voltage is 0.18 because it is nothing but 0.18 denotes the 10% of the uh, final steady state value. So here you can cancel out the term A, and you can take a ln on both sides. You simplify. Finally you will calculate the value of T as 0.1 RC. Similarly, in order to calculate how much amount of time the output response is taking to achieve the 90% of the final value, in order to calculate that, here instead of the same analysis you are going to repeat, but instead of 0.1 you need to substitute 0.98, and you simplify like taking ln on both sides. You do simplification. Finally you will end up with t value as 2.3 into RC. Now, what is a rise time? According to the definition, it is a time required for the output response to jump from 10% of the steady state value to 90% of the steady state value. So this is the time required for 10%, and this is the time required for the output response to reach 90%. So we subtract these two values and you'll end up with the rise time as 0.22 RC. We know that RC is nothing but a time constant, so this can be replaced by tau. Now you know the relation between cutoff frequency uh, and the RC. So F2 equal to 1 divided by 2 pi RC. Here RC you can replace by tau. So you can write F2 equal to 1 divided by 2 pi tau. From this you can write tau equal to 1 pi 2 pi into F2. So here I am going to replace this tau by 1 by 2 pi F2. Now you can simplify this analysis so that finally you will be having and that rise time is nothing but 0.35 divided by F2. So if you know the cutoff frequency, you can easily calculate the rise time. So that's all about the analysis. Thank you.